Hello, everyone. My name is Qais Amarkhil, and I'm a PhD student at Purdue University and working under Professor Emad Elwakil and Professor Bryan J. Hubbard at Purdue University. And now our research topic is toward integrated scheduling approach, which is a location and activity-based scheduling. And I am presenting on behalf of our research team. So what's a schedule and why it's needed in construction? So we all know it. We need a plan for any kind of construction work, and we need to link it with time and resources, and we call that in construction a schedule. And the purpose for that is to complete a project within desired time, and have a better productivity, and to know how to do the job. So this is why the construction project schedule has been the topic of interest since a long time ago, maybe even more than a century in its scientific form. And from the literature, I classified the primary scheduling techniques in two major groups. One is traditional and location-based scheduling approach, which shows in table 1, and the other one is activity-based, which is called network scheduling techniques. So the traditional one is more concentrated on Gantt chart, milestone, linear scheduling, which is a location production, or a line of balance, which is unit production. On the other hand, activity-based scheduling techniques are critical path method. They are using maybe like activity on arrows or activity on nodes, or then the later revision to that approach is the precedence diagram method, or even further they have developed to include uncertainty to it. They used program evaluation and review technique, or graphical evaluation review technique. But all of these techniques has some advantages and disadvantages. So what's now state of the art and recent years? So the state of the art is, and since past few decades, by the development or advancement in the technology, researchers have started to overcome the disadvantages of those scheduling approach that already exist, and they started using machine learning algorithms and priority rules to auto-generate a schedule. But the question is, do these machine learning algorithms, priority rules, or whatever that has been studied or researchers want to improve, help the applicability of the construction project in practice? I have here a diagram of, or a flow chart of generating a construction project automatically from a BIM authoring model. So here it explains how it can be generated from a BIM model by using its geometry data and material data and putting it in a system, and then to have a schedule and MS project. So the outcome is still the same thing that we are practicing it more than a century. So it seems it won't help the limitation or the challenge that now, or even since long time, we have it in the construction industry, which is like the construction project delay or need for to further improve productivity. And from the literature review, I just shortlisted few points like insufficient defined activity dependency, limited ability to auto-generate activity, activity-based methodology, unable to consider congestion and location, lack of location and technology-based methods, unable to consider external factor and constraint and limitation, limited ability to optimize schedule. These are some of the points that are not addressed well. So this is why the object of our study is to improve the construction project applicability in practice and in order to minimize project delay, and also to help or easily integrate it with new technology to auto-generate a project schedule. So we summarized the methodology in 10 steps, and the first step is to define activities and working spaces. The way we see it, this paper specifically focus on vertical structures because of the difference it has with other kind of construction or non-construction project. So we define activities and working spaces. And for that, we divide the total number of activities into major categories. One is activities that can be, or the work that can be done on open spaces like site and building envelope from outside, or building cladding and roof, which does not need the environment to be a closed space to do the activity. And the other group is spaces where the work is done in closed spaces like floors, levels. And the second step is to differentiate or separate activity based its nature, like we call it one directional activity, which are only limited to one working space, like maybe a floor, and two directional activity that is not only limited to one working space, but it's needed for another work space, like maybe we have, maybe we can consider an activity that's needed for N floor, but at the same time, we needed to have it for the N+1 floor as well, maybe one of like structural activity or something. The remaining relationship and notation are much similar to the precedence diagram method. I'm not going to explain it here in detail, and just going to the third step. And here you can see in step 1 and 2 in that building how it look like to define it. And then the step 3 is after like we define activity in its relevant working spaces, then we need to establish the interdependency in each specific working space. So here we have from, for example, we name it from Z0 to Zn working spaces, and each working spaces we define the interdependency of activities, like which is the precedence in precedent or successor activities. And the fourth step is to identify two directional activities. It means like the activity that's not only critical for the working space where that activity is located, but it's also critical and required for the immediate neighbor working space. Like without doing the precedent or predecessor activity, the successor activity cannot start in the next working space. And the fifth step is to draw the network of those two directional activity. And in this stage, we just do not work on the one directional activity for the ease of like developing or creating the schedule. Then in step 6 and 7, we are once we draw the network of two directional activity, we start to connect the one directional activity in each working space to two directional activity that is located in the same working space with those activity and those one directional activities. And step 8, 9, and 10 is once we connect or draw all the network, we find the longest or the lengthiest working space that takes the maximum time, which is the project completion date. And we do the backward calculation from that point and identify three types of activities: project critical activity, which is shown in orange color, then a level critical activity we just showed here in blue color, and non-critical activity was shown in green color. So to further explain this approach, we did a sample project. We choose some randomly activities and we built the interdependency between these and did the calculation for that. Here, the example is for a two-story building. Z0 represent the site, and Z1 and Z2 represent the two floors, interior spaces, and roof and its envelope. Here you can see what we have done. First, we put activity in each relevant working space. Then we built the relationship between the two directional activity, which are shown in red color. And then once we did this, we connect activities in each working space to the two directional activity. And you can see only the two directional activities relationships are connected from space to from one.
Just one more minute, Mr. Amarkhil, just one more minute.
So to another working space. So in this approach, we also have technological relationships that also, if we have some constraints of resources or technology, can account for that. So here we can see, in addition to the free float and total float, we can have project float as well. So here, what calculation we have done, we find the working space, which is building envelope, has the 66th latest completion date, which is here we take it as a project completion, and we did the backward calculation. So we find out here in step 2 that these two directional activity, however, it's critical for the flow for the working space roof, but it can have 4 days project completion time, and totally opposite to that, here an activity which is normally in the critical path method has 4 days, has 6 days free float and 6 days total float, but in this approach it shows only 2 days project completion float, which means we cannot delay it more than 2 days if we consider the resource constraint. However, it's non-critical based on the critical path method. So the conclusion is this approach can improve the project applicability, minimize delays, measure impact of constraints, perform work in different spaces, because we do not need to always do it from down to top or top to down. We can just consider the project floor float, and we can plan it, the work from that place. And it's also more in compliance with what's BIM and other technology does to auto-generate a project schedule. And here is a quick review of the main elements that we used: one directional activity, two directional activity, project critical path, working spaces critical path, total float and free float, working space float, and resource and technology constraint, and external impacting factors. These elements are easy to consider in this approach. And here I end my presentation. Thank you. And if you have any questions, so I will be happy to answer.
Thank you so much.